Okay, so what we're going to look at today is some applications of systems of equations. I'm going to give you a little bit of background. What I have up here right now is actually called a phase diagram. This is a single substance phase diagram. Shrink it just a little bit to make it visible. Every substance has a phase diagram like this. We're used to every substance that we encounter has solid, liquid, and gaseous states, right? So somewhere around here is what we call atmospheric pressure. If I draw that line flat across there, pretend it looks flat. And by atmospheric pressure, I mean the pressure that we experience, in the real world without any sort of decompression or compression being applied. Now we know that that's not just a little line across there, it's actually a band, because atmospheric pressure can go up or down a little bit. Well, and you can see what happens here. What's going on here is this is the line between solid and liquid, and this is temperature down here. So the transition between solid and liquid, that transition temperature is relatively stable for most substances. So if atmospheric pressure goes down a little bit, the temperature at which water freezes, or whatever substance freezes from a liquid to a solid, or melts from a solid to a liquid, doesn't change much. And we experience this with water here. I mean, you go from here, where we're not too far above sea level, to Denver, Colorado, where they're a little over a mile above sea level. The temperature at which water freezes doesn't change much. This line down here is the transition between liquid and gas. And you can see that line has a little bit more slant to it. So that range of atmospheric pressure, there's a bigger difference. At higher atmospheric pressure, and I'm just going to say that this is water right now. I don't know exactly what substance this really is, but it's a theoretical substance. At the higher atmospheric pressure, which is where we're at, water boils, goes from liquid to gas, about 212 degrees Fahrenheit or 100 degrees Celsius. But you reduce that atmospheric pressure a little bit by going to, Colorado, up higher altitudes, lower atmospheric pressure. You can see that temperature drops considerably. In Denver, Colorado, especially on a very clear day where it's low pressure, you can boil water at like 175 degrees. I mean, it'll drop 30 or 40 degrees in what the temperature of boiling water is. So that transition from liquid to gas is much more sensitive. You can see here something called a triple point. Every substance has those. And what that is, that's the temperature at which, or the pressure at which, if the pressure falls below that, that substance will not have a liquid state. It will go straight from gas to solid. And that pressure is different for every substance. Most substance, that pressure is very, very low. So if we took water and we lowered the pressure, we put it in a container and we sucked the air out of it to lower the pressure, we would actually see it go from solid straight to a gas. There'd be no liquid state of water. Every substance has that state where if you get to a low enough pressure.
Say that again?
If we put it in a glass container and suck most of the air out of it, so it's really low air pressure, like a vacuum chamber, exactly. You have it frozen in ice. As you heat it up, it would not melt to water. It would go straight from ice to water vapor to gas.
Oh, okay.
Now, do we know of any substances that do that at atmospheric pressure? There's one main one that most of you have probably seen. Dry ice. Carbon dioxide. The triple point for carbon dioxide is actually above atmospheric pressure. So everybody says carbon dioxide does not have a liquid state. It does, but you actually have to put it in a pressurized area. If you pressurize it, it will have a liquid state. And you can see here, the more pressure, the wider that liquid state is. At higher pressure, that liquid state is in a wider range of temperatures. But you can, if you pressurize it, you can force carbon dioxide to have a liquid state at a small band of temperatures. Now, water does go straight from solid to a gas around us every day. In fact, it's doing it outside probably this afternoon. They'll be doing it. It'll go directly from snow into water vapor. Like, well, atmospheric pressure isn't low. Well, what happens is moving air causes low atmospheric pressure. That's the theory behind an airfoil or airplane wing, is it's actually shaped like this. It's flat, relatively flat on bottom and rounded on top. So air that goes over the top has further to go than air that goes on bottom. So the air on top has to move faster to get over it. And since it's moving faster, it's low pressure and it creates lift. So outside right now, as I said, there's that snow going directly from a solid snow to gas, to water vapor. It's because there's wind blowing. And it'll happen especially where you have a snow plowed. As the wind comes over that, and comes back, it's going to create a low pressure area back here. And that'll actually evaporate. They call it, when it goes straight from a solid to a gas, it's actually called sublimation. So it's going to sublimate directly from snow into the air, even though it's not warm enough to melt.
Is that why? Never mind.
No, go ahead.
No, it's not. It's not relevant.
Okay. So every substance has one of those. This is actually the water diagram right here. This is 1 atmospheric pressure. 1 atmosphere is considered standard atmospheric pressure at sea level. I can't remember. It's at a given humidity and temperature, and I can't remember exactly what that is right now, but it is there.
Why is it so dry in wintertime?
Why is it so dry? Well, it's because of dew point. It's too cold for the air to hold too much water, so it's dry. The warmer it is, the more water the air is capable of holding. The colder it is, the less it is. So it's cold enough that it just can't hold that much air or that much water. The triple point for water is at 6 thousandths atmospheric pressure. So it's less than 1% of standard atmospheric pressure. It would have to be sucked down that far. See, there's something called a supercritical point up here. You saw it up here, the supercritical region. If you get it to a high enough temperature and a high enough pressure, it cannot expand into a gas. And that's where you've heard there's that 4th state of matter called a plasma. And that's what happens in that region, is it becomes a plasma. But it only exists at either extremely high temperatures or extremely high pressure. And it needs high temperature to go with the pressure. Plasma is really weird. It's like everything becomes electrically conductive when it turns into a plasma. It's just a really weird state. So that's water vapor. And this is just other possible diagrams for different possible substances. So we're not going to go through those.
So
Here's.
this might be retarded, but is that why you get frost on your windshield? Just because the dew drops?
Yeah, it's actually,
Freezes,
your glass is colder than the air.
Humidity
drops
Yep.
onto your vehicle.
condenses on the glass.
Yeah. Okay.
Yeah, is that your glass is colder than the air. And so when the warm air hits it, the air is close to its dew point as it is. So it's barely warm enough to hold the air that's in it. It hits your windshield, which is colder, and it can't hold the water, so it has to drop the water there. When it's really cold, it drops the water and instantly freezes. Now, the reason you get those weird swirls and stuff in the winter sometimes is it's actually cold enough to freeze it directly. It doesn't condense to water first. I mean, usually you get just a sheet of frost. The air is hitting it. It's too cold to hold the water vapor anymore, so it condenses to water and then freezes. But you get those funny little swirls. The windshield, the glass is actually cold enough that it goes straight from water vapor into a solid. It skips that water stage, the liquid
So why
stage.
am I getting icicles off my roof? 'Cause
That's
the
just
bottom
drips.
snow's melting.
Now there's snow on the top. It's running down and it's dripping and freezing as it drips. That's all those icicles are.
If there's enough ice, that is actually handy. You don't melt the stuff on the bottom.
That's what.
Yep.
And then it just comes down my.
Well, then it just goes down the top of it, it's like big glaciers and stuff like that.
That's actually how snowflakes form too. Is the difference between sleet and snow. Sleet, it's cold enough that the clouds can't hold the moisture anymore, so it drops the moisture as water and it freezes on its way to the ground. That's where you get the ice balls. Snow, the clouds actually encounter a cold enough blast of air that if the water vapor freezes directly from vapor to solid. And that's why you get the snowflakes. That geometric pattern is the form of the vapor freezing. Okay, so the reason I showed you that is I wanted to get to this here. This is what is called a binary phase diagram. This is one of the simpler ones we have. This is copper nickel. The iron carbon phase diagram is quite complex. See if I've got one. This is a, can't remember what this one was. This is just, it's a little bit more complex phase diagram, but this is what they call a eutectic point. This one could, it's got the proper form, but it doesn't line up with the right percentages. Could be the lead tin phase diagram for solder. The lead tin phase diagram, that eutectic point would be in the 60s. Depending on your type, your isotopes, I believe it's 62 is your eutectic point for lead tin, if I remember correctly. But the eutectic point means it goes straight from solid to liquid and there's no mush stage. When you have an alloy of two metals, that melting, each substance has a different melting point. So what happens is the one substance melts here, the other substance melts at this temperature. So as you melt it, it partially turns to mush. It doesn't go straight from solid to liquid. Most pure substances, as you melt them, they'll be solid. They might get soft for just like a tenth of a degree, but then they turn straight to a liquid. They don't have a mush stage. Alloys, where you're mixing two metals together, will have a mush stage where it's partially melted with solid chunks floating in it. And that is what this diagram is talking about or demonstrating, is at a 2080 composition here, at this temperature, which looks to be about 1230, 1240 degrees, it will start to melt. Part of it will melt. At this temperature, which is about 1360, it looks like, it'll all be melted. It'll be all liquid. In between there, it's going to be some solid, some liquid. It's going to be mush. At this mixture, which looks to be about 50-50, it goes straight from solid to liquid. There's no mush stage. But as you get more in there, it goes back to having a mush stage in it. And we're going to describe that mush stage here in a little bit. This is actually what I was saying was the lead tin at 61.9 or 62% basically tin, 38% lead. You have that eutectic point, go straight from solid to liquid. Anybody in here ever done any soldering? Yeah. You'll notice, I mean, you got the iron on it, it's heating up. The end of the wire might be getting a little mushy, but then all of a sudden it's liquid. It just like lets loose. That's because you get it to that temperature, which is just under 200 degrees. It's actually 183 degrees Celsius. It goes directly from solid to liquid when you hit it at that temperature, because it is 62% tin, 38% lead. The new lead-free solder doesn't work so nicely. It has a little bit of a mushy stage in it. If you don't get it hot, you got to heat it up real quick. This is atomic tin. We're not gonna look at that. This is actually iron graphite. I want to look. Here is the iron carbon diagram. You can see it's much more complex. Right here at about 4.3% carbon, there's a eutectic point where it goes straight from being solid to melted. There's another eutectoid point here. We're not going to get too far into that diagram. It's a little bit more complex than I want to talk about here, but we're just going to do it with the math. I just wanted to show you that, to show you that the copper nickel one we're working with is an extremely simple binary phase diagram. The reason it's binary is because we're combining two substances. So what does this diagram tell us? What it is telling us, this side here is pure copper. Pure copper melts at 1,085 degrees. It will go directly from a solid to a liquid when it hits that temperature. This is pure nickel here. Pure nickel melts at 1,455 degrees. As we mix them together, that melting point changes. At 40%, this would be a 40% nickel, so 60% copper. We trace that up. Now, let me do it the right way. I'm going to take a line here. Okay, it's a little thicker so you can actually see it. So there's that line there going straight up at, there we go. That is 40% nickel, 60% copper. And you can see, I'm just going to do this.
You mean 40% copper, 60% nickel?
No, this is the percent nickel down here. 0% is 100% copper, 0% nickel. This is 20% nickel, 80% copper. This is 40% nickel, 60% copper here. So what's happening here, I'm just going to try to line this up. That looks to be right on that bottom line there. At that mixture, 40% nickel, 60% copper, it starts to melt. It is the whole thing is completely solid up until that point. So that looks to be just below 1250, about maybe 1240, I'd call it. 1240 degrees, it is completely solid. Then it starts to get that mush. Between that temperature and this one up here, that looks to be crossed right about where that top border of that region is. That looks to be, what, about 1280, 1285 maybe. At 1285 degrees, above that, it's going to be totally liquid. It's in between there, in between 1240 and 1285. It's going to be a mush. The composition of that mush is actually kind of interesting. And it depends on the temperature. Let's say the temperature is 1250 degrees right there. What we're going to have is two substances here. One substance is going to occur on this boundary where the temperature crosses that. This is going to be the liquid portion of it. The liquid portion, you can see here, is only going to be like 31% nickel and 69% copper. Over here on this boundary, see where's the 1200? So it crosses right about there. That's going to be, what, about 44% nickel? So 56% copper? Do you see what I'm saying? Let me pull my pen back up here. So what we're getting here is, this line right here is what temperature we're at. 1250 degrees. So at that temperature, we cross across here. There's going to be liquid, because this is the liquid side. There's going to be liquid right there, that composition. And there's going to be solid right there, because this is the solid side here, that composition. Because that's where that temperature line cuts through those regions. So what does this have to do with what we've been talking about? Well, here it is, right here. Let's say we had 1,000 grams of our original material. So here's what we had. Let's go back here. We had 1,000. Our original material was 40% nickel, 60% copper. If we had 1,000 grams of that, that means 0.4 times 1,000 is 400 grams of nickel. And 0.6 times 1,000 is 600 grams of copper. Does that make sense so far? So what we want to figure out right now is how much of that 1,000 grams is liquid and how much of that 1,000 grams is solid. Well, the liquid right here, what would you call that down there? About 31%? Does that look right? Is it 31? So our liquid, come on. The liquid looks to be 31% nickel, so that make it 69% copper. So the solid, what does that look like down there? About 44. That's 50, so 44% nickel. So that looks to be 44% nickel and 56% copper. We know there's 400 grams of nickel. So we're going to write an equation to describe the nickel. There's 400 grams of it. So we're going to let X be the amount of liquid, Y be the amount of solid. 31% of the liquid is nickel. So that's 0.31 times X. 44% of the solid is nickel, so that's 0.44 times Y. The total amount of nickel can't change. We still have to have 4,400 grams of nickel. Our second equation is going to describe the copper. There is a total of 600 grams of copper. Well, in the liquid, it's 69%. So that's 0.69 times X is the amount of copper in the liquid. In the solid, it's 56%. So that's 0.56 times Y is the amount of copper in the solid. We have a system of equations to solve here. So to solve this system of equations, I'm going to use the elimination method, or the addition method, if you want to call it that. But I'm going to take a slightly different approach. What I am going to do is, instead of multiplying the equations, I'm going to divide them. Because let's face it, if I look at this 0.31 and 0.69, what's the least common multiple of that? Who the heck knows, right? So I'm just going to pick one of my variables and turn them both into 1. So I'm actually going to eliminate my y here. And the way I'm going to choose to eliminate my y is I'm just going to divide by that coefficient. Coefficient of y here is 0.44, so I'm going to divide this by 0.44. So that's going to give me 400 divided by 0.44. 909.09. 0.31 divided by 0.44. 0.7045, we'll call it. X. 0.44 divided by 0.44 is 1, so that's a positive 1y.
Why are you dividing?
Because I need to get these two the same so that they'll cancel out when I add them up.
Okay.
But trying to figure out what to multiply them by is a real bear, so I'm just going to divide them out. That's the same as when we multiplied both equations. Yeah, you can do that every time. It gives you some ugly decimals, so there's going to be some round off error, but we can do it every time. This one down here, what am I going to divide this one by? If I want to turn that into a 1, it would be 0.56, right? But I'm not going to divide by 0.56, I'm going to divide by negative 0.56. Why am I doing that? I want this to be a negative 1. That's why here. 0.56 divided by negative 0.56 is a negative 1. I want it to be a positive 1 and a negative 1, so when I add them, they cancel out. So 600 divided by 0.56, actually negative 0.56, is going to be a negative 1071.43. Negative 0.69 divided by negative 0.56. So 0.69 divided by negative 0.56 is a negative 1.232 x. And then they got the negative 1y. So now you can see this looks like our equations we had yesterday, or actually 2 days ago, actually last Friday. If I add my columns, I've got 909.09 plus a negative 1071. So I get a negative 162.34 there. Over here, 0.7045x. I'm going to take that another digit here. 0.7045x plus a negative 1.2321. I'm going to do that one on the calculator. It's going to give me negative 0.5276. X. Then, of course, the 1y and negative 1y cancel out. So to solve this, I'm going to divide by the negative 0.5276. This is all exactly what we did last Friday. It's just a lot uglier numbers because we have all the ugly decimals in there is all. So we're going to take a negative 162.34 divided by that previous answer, the negative 0.5276. Gives me 307.70 we're going to call it. That equals x. Remember, x was the amount of liquid. So 307.70 grams of this is liquid. Now to find the other substance, by the way, I could go ahead, I could put that 307.70 in one of these for x and solve it. But I know there's how many total grams? 1,000 total grams, right? This is 600. 692.30 grams of solid. So you can actually calculate your separation. Now, what is this good for? Well, let's say you have that 40-60 alloy, 40% nickel, 60% copper alloy that we just talked about. And you want to adjust it a little bit. Let's say you want it to be 50-50. What you can do is this. I'm going to move this line here over so it's 50%. I'm going to take this line up to where it crosses. So you can see what happens right there is where that blue line crosses the bottom of that region. So this is telling me what temperature. If I take this up to, that looks to be about 1275 degrees. If I take this up to 1275 degrees, and then I scoop out the chunks that are still solid, those solid chunks will be 50% nickel, 50% copper. Now, do you think there's going to be a lot of it there? No, that's the further you get away from this original line, the less of it there's going to be. There's going to be just a very few solid chunks in there, but those solid chunks at that temperature will be 50-50. So this is a way you can actually take an alloy by using this diagram. You can heat it up and partially melt it and separate out the solid portion from the liquid portion to adjust the mixture of the alloys. Now I realize this is a pretty complex concept and we just kind of jumped into it. The important part here is being able to solve the system of equations. Now tomorrow, we will have a unit test. This would be an extra credit question on your unit test, just so you know. So I'm not expecting you guys to have this mastered after talking about it for a day. But you'll have a possibility to earn some points by being able to do it. It is pretty confusing. There's a lot of information here.
What
But-
else does the unit test go over?
What all the unit test score goes graphing lines. Also for non-lines, just filling in a table and plotting points. Solving equations, solving systems of equations. That's basically it. Word problems. This unit test is a tough one, but it's not. I think the last one with all the surface areas and volumes was tougher. Anybody have any questions on this? All right. You guys actually used to